Learning objectives. In this chapter, the user would learn the following in detail. Basic MAC protocol, CSMA-CA. Infrastructure and ad hoc network topologies, MACA. MACAW. Use of PCF. IEEE 802.11 standards. Hyperlan, IRDA, Bluetooth, Zigbee. The basic access method, CSMA/CA. The basic access mechanism, called the Distributed Coordination Function by IEEE standard, is Carrier Sense Multiple Access with Collision Avoidance Mechanism, CSMA/CA. The most popular CSMA protocol is the Ethernet, which is a CSMA/CD protocol. CD stands for collision detection. In a wired environment, Ethernet for example, every station connected to the wire can sense the signal in the wire. In a wired LAN, if there is no activity or a collision of messages, every station connected to the LAN will be able to sense the collection almost instantly. In the case of wireless LANs, a carrier sense multiple access or collision avoidance CSMA/CA protocol is used, as it is not possible to detect a collision of data packets in mid-air. Hidden terminal. Consider the scenario with 3 mobile nodes as shown in figure. The transmission of A reaches B but not C. The transmission of C reaches B but not A. However, the radio signal of B reaches both A and C, making A and C both in the range of B. The net effect is A cannot detect C and vice versa. A starts sending to B, C does not receive this transmission. C also wants to send to B and senses the medium. To C, the medium appears to be free. Thus, C starts sending, causing collision at B. But now, A cannot detect the collision and continues with its transmission. A is hidden for C and vice versa. Exposed terminal. Consider another case as shown in figure above. The radio transmission signal of A reaches C and B. The radio signal of C reaches both A and D. A wants to communicate to B. A starts sending signals to B. C wants to communicate with D. C senses the carrier and finds that A is talking to B. C has to wait till the time A finishes with B. However, D is outside the range of A, therefore waiting is not necessary. In fact, A, B and C, D can communicate with each other in parallel without any collision, but according to the protocol, that is not possible. A and C are exposed terminals. The basic access method, CSMA/CA. While collision detection mechanisms cannot be used on a wireless LAN environment for 2 main reasons, implementing a collision detection mechanism requires the implementation of a full duplex radio capable of transmitting and receiving at the same time. This increases the cost significantly. In a wireless environment, we cannot assume that all stations will be able to receive radio signals from each other, which is the basic assumption of the collision detection scheme. The fact that a station wants to transmit and senses the medium as free, not able to sense signal from another station, does not necessarily mean that the medium is free, like the case of the hidden terminal around the receiver area. CSMA/CA mechanism. When a wireless station, a wireless LAN device, wants to communicate, it first listens to its media radio spectrum to check if it can sense radio waves from any other wireless station. If the medium is free for a specified time, then the station is allowed to transmit. This time interval is called Distributed Interframe Space, DIFS. If the current device senses a carrier signal of another wireless device on the same frequency as it wants to transmit on, it backs off, does not transmit, and initiates a random timeout. After the timeout has expired, the wireless station again listens to the radio spectrum, and if it still senses another wireless station transmitting, it continues to initiate random timeout until it does not detect or sense another wireless station transmitting on the same frequency. When it does not sense another wireless station transmitting, the current wireless station starts transmitting its own carrier signal to communicate with the other wireless station, and once synchronized, transmits the data. The receiving station checks the CRC of the received packet and sends an acknowledgement packet ACK. Receipt of the acknowledgement indicates to the transmitter that no collision occurred. If the sender does not receive the acknowledgement, then it retransmits the fragment until it receives acknowledgement or is abandoned after a given number of retransmissions. Virtual carrier sense. In order to reduce the probability of two stations colliding because they cannot sense each other's presence, the standard defines a virtual carrier sense mechanism. A station wanting to transmit a packet first transmits a short control packet called RTS, request to send, which includes the source, destination, and the duration of the following transaction, the data packet and the respective ACK. The destination station, after receiving this request, packet responds with a response control packet called CTS, clear to send, which includes the same duration information. All stations receiving either the RTS and or the CTS set their virtual carrier sense indicator called network allocation vector or NAV for the given duration and use this information together with the physical carrier sense when sensing the medium. This mechanism reduces the probability of a collision on the receiver side by a station that is hidden from the transmitter to the short duration of the RTS transmission because the station senses the CTS and reserves the medium as busy until the end of the transaction. The duration information on the RTS also protects the transmitter area from collisions during the ACK from stations that are out of range of the acknowledging station. It should also be noted that due to the fact that the RTS and CTS are short frames, the mechanism also reduces the overhead of collisions since these are recognized faster than if the whole packet was to be transmitted. The figure below shows a transaction between stations A and B and the NAV setting of their neighbors. Bluetooth. Bluetooth was the nickname of a Danish king, Harald Blædende, who unified Denmark and Norway in the 10th century. The concept behind Bluetooth wireless technology was unifying the telecom and computing industries. This technology allows users to make ad hoc wireless connections between devices like mobile phones, desktop or notebook computers without any cable. Devices carrying Bluetooth-enabled chips can easily transfer data at a speed of about 1 Mbps in basic mode with a 50-meter, 150 feet range or beyond through walls, clothing, and even luggage bags. Bluetooth protocol. Bluetooth uses the unlicensed 2.4 GHz ISM industrial, scientific, and medical frequency band. There are 79 available Bluetooth channels spaced 1 MHz apart from 2.402 GHz to 2.480 GHz. IEEE has adapted Bluetooth as the 802.15.1a standard. Allows power levels starting from 1 MW covering 10 cm to 100 MW covering up to 100 meters. These power levels are suitable for short device zone to personal area networks within a home. Supports both unicast point-to-point and multicast point-to-multipoint connections. Bluetooth protocol uses the concept of master and slave. Master-slave protocol. A device needs to wait till the time the master allows it to talk. The master and slaves together form a piconet. Up to 7 slave devices can be said to communicate with the master. Several of these piconets can be linked together to form a larger network in an ad hoc manner. The topology can be thought as a flexible multiple piconet structure. This network of piconets is called scatternet. Scatternet. Scatternet is formed when a device from one piconet also acts as a member of another piconet. In this scheme, a device being master in one piconet can simultaneously be a slave in the other one. Bluetooth protocol. Bluetooth protocol is a combination of different protocols. The Bluetooth core protocols plus the Bluetooth radio protocols are required by most of the Bluetooth devices, while the rest of the protocols are used by different applications as needed. At the physical layer, Bluetooth uses spread spectrum technologies. It uses both direct sequence and frequency hopping spread spectrum technologies. Bluetooth uses connectionless ACL, asynchronous connectionless link, and connection-oriented SCO, synchronous connection-oriented link links. Together, the cable replacement layer, the telephony control layer, and the adopted protocol layer form application-oriented protocols, enabling applications to run over the Bluetooth core protocols. Bluetooth protocol stack. A combination of multiple application-specific stacks as depicted in figure. Different applications run over one or more vertical slices from this protocol stack. These are RF COM radio frequency communication, TCS binary telephony control specification, SDP service discovery protocol. Each application environment uses a common data link and physical layer. RF COM and the TCS binary telephony control specification protocol are based on ETSI TS07.10 and the ITU T recommendation Q.931 respectively. L2 CAP Logical Link Control and Adaptation Protocol or TCS may use LMP Link Manager Protocol to control the link manager. Bluetooth protocol stack can be divided into 4 basic layers according to their functions as given below. Bluetooth core protocols. This comprises of baseband, Link Manager Protocol LMP, Logical Link Control and Adaptation Protocol L2CAP, and Service Discovery Protocol SDP. Baseband. The baseband and link control layer enables the physical RF link between Bluetooth units forming a piconet. This layer uses inquiry and paging procedures to synchronize the transmission with different Bluetooth devices. Using SCO and ACL link, different packets can be multiplexed over the same RF link. ACL packets are used for data only, while the SCO packet can contain audio only or a combination of audio and data. All audio and data packets can be provided with different levels of CRC, cyclic redundancy code, or FEC, forward error correction, for error detection or correction. Link Manager Protocol LMP. When two Bluetooth devices come within each other's radio range, link managers of either device discover each other. LMP then engages itself in peer-to-peer message exchange. These messages perform various security functions starting from authentication to encryption. LMP layer performs generation and exchange of encryption keys as well. Performs the link setup and negotiation of baseband packet size. Also controls the power mode, connection state and duty cycles of Bluetooth devices in a Piconet. Logical Link Control and Adaptation Protocol L2CAP. This layer is responsible for segmentation of large packets and the reassembly of fragmented packets. L2CAP is also responsible for multiplexing of Bluetooth packets from different applications. Service Discovery Protocol SDP. The Service Discovery Protocol SDP enables a Bluetooth device to join a Piconet. Using SDP, a device inquires what services are available in a Piconet and how to access them. SDP uses a client-server model where the server has a list of services defined through service records. One service record in a server describes the characteristics of one service. In a Bluetooth device, there can be only one SDP server. If a device provides multiple services, one SDP server acts on behalf of all of them. Similarly, multiple applications in a device may use a single SDP client to query servers for service records. A Bluetooth device in an inquiry mode broadcasts ID packets on 32 frequency channels of the inquiry hopping sequence. It sends 2 ID packets every 625 µs and then listens for response the following 625 µs. At this stage, the unique identity of the devices called Bluetooth Global ID is exchanged. A global ID indicates a device's profile along with capability functions. Upon matching of the device profile, a connection is set up and devices exchange data. When a connection is set up, the paging device becomes the master and the paged device becomes the slave. In a Piconet, a master device can be a laptop or PDA, while slaves' devices could be printers, mouse, cellular phones, etc. Cable Replacement Protocol. This protocol stack has only one member, viz. Radio Frequency Communication (RFCOM). RFCOM is a serial line communication protocol and is based on ETSI 07.10 specification. The Cable Replacement Protocol emulates RS-232 control and data signals over Bluetooth baseband protocol. Telephony Control Protocol. This comprises two protocol stacks with Telephony Control Specification Binary TCS-BIN and the AT commands. Telephony Control Protocol Binary. TCS Binary or TCS-BIN is a bit-oriented protocol. TCS-BIN defines the call control signaling protocol for setup of speech and data calls between Bluetooth devices. It also defines mobility management procedures for handling groups of Bluetooth TCS devices. TCS binary is based on the ITU-T recommendation Q.931. AT commands. This protocol defines a set of AT commands by which a mobile phone can be used and controlled as a modem for fax and data transfers. AT, short form of attention. Commands are used from a computer or DTE, data terminal equipment, to control a modem or DCE, data circuit terminating equipment. AT commands in Bluetooth are based on ITU-T recommendation V.250 and GSM 07.07. Adopted protocols. This has many protocol stacks like Point-to-Point Protocol PPP, TCP IP Protocol, OBEX Object Exchange Protocol, Wireless Application Protocol WAP, vCard, vCalendar, Infrared Mobile Communication IRMC, PPP Bluetooth. This offers PPP over RFCOM to accomplish point-to-point connections. Point-to-point protocol is the means of taking IP packets to and from the PPP layer and placing them onto the LAN. TCP/IP. This protocol is used for communication across the Internet. TCP/IP stacks are used in numerous devices, including printers, handheld computers, and mobile handsets. Access to these protocols is operating system independent, although traditionally realized using a socket programming interface model. TCP/IP PPP is used for the all-internet bridge usage scenarios. UDP/IP PPP is also available as transport for WAP. OBEX protocol. OBEX is a session protocol developed by the Infrared Data Association (IRDA) to exchange objects. OBEX provides the functionality of HTTP in a much lighter fashion. The OBEX protocol defines a folder listing object, which can be used to browse the contents of folders on remote devices. Content formats. vCard and vCalendar specifications define the format of an electronic business card and personal calendar entries developed by the Versit Consortium. These are now maintained by the Internet Mail Consortium. Other content formats supported by OBEX are vMessage and vNote. They are defined in the IRMC/IRDA Mobile Communication Specification. IRMC also defines a format for synchronization of data between devices. Bluetooth security. In a wireless environment where every bit is on the air, security concerns are high. Bluetooth offers security infrastructure starting from authentication, key exchange to encryption. In addition to encryption, a frequency hopping scheme with 1600 hops per second is employed. All of this makes the system difficult to eavesdrop. At the lowest levels of the protocol stack, Bluetooth uses the publicly available cipher algorithm known as SAFER+ to authenticate a device's identity. In addition to these basic security functions, different application verticals use their own security infrastructure at the application layer. Bluetooth application models. File transfer. The file transfer usage model offers the ability to transfer data objects from one device, example PC, smartphone, or PDA, to another. Object types include .xls, .ppt, .wav, .jpg, .doc files, folders or directories, or streaming media formats. Internet bridge. In this usage model, a mobile phone or cordless modem acts as a modem to the PC, providing dial-up networking and fax capabilities without need for physical connection to the PC. LAN access. In this usage model, multiple data terminals use a LAN access point (LAP) as a wireless connection to an Ethernet LAN. Once connected, the terminals operate as if they were connected directly to the LAN. Synchronization. The synchronization usage model provides a device-to-device, phone, PDA, computer, etc. synchronization of data. Examples could be PIM, Personal Information Management information, typically phone book, calendar, message, and note information. Headset. The headset can be wirelessly connected for the purpose of acting as a remote device's audio input and output interface. This is very convenient for hands-free cellular phone usage in automobiles. HyperLAN. HyperLAN is a European counterpart for the Wireless Local Area Network. It stands for High Performance Radio Local Area Network. HyperLAN is a family of standards developed in Europe by BRAN project Broadband Radio Access Networks of ETSI. It defines interoperability standards which specify a common air interface (MAC) and physical layers in OSI model. Figure shows the stack relationship of HyperLAN with OSI layers. It is equivalent to wireless LAN defined by IEEE 802.11 standards. The physical layer and the media access control part of the HyperLAN data link layer are like 802.11 standards. There is a new sublayer called Channel Access and Control (CAC) sublayer which deals with the access request to the channels. The request is served depending upon the usage of the channel and the priority of the request. CAC layer provisions hierarchical independence with elimination yield non-preemptive multiple access mechanism EY-NPMA. EY-NPMA codes priority choices and other functions into one variable length radio pulse preceding the packet data and helps network to function with lesser collisions even when there are a large number of users. Transitively, multimedia applications work better in HyperLAN because of EY-NPMA priority mechanism. HyperLAN MAC service. Compatible with the ISO MAC service definition. Defines the communication service over a single HyperLAN. Allows the timing requirements of the MAC service data unit MSDU transfer to be specified. Allows the exploration of available HyperLANs for dynamic HyperLAN access. HyperLAN CAC service. Defines the communication service over a single shared communication channel. Allows the channel access priority requirements of the HyperLAN CAC service data unit HCSDU transfer to be specified. Frees the HCS user from the concerns of the characteristics peculiar to any particular communication channel. HyperLAN MAC protocol. Provides the HyperLAN MAC service. Specifies the behavior of a HM entity in a given HyperLAN. Compatible with the ISO MAC bridges specification. Uses the HyperLAN CAC service. HyperLAN CAC protocol. Provides the HyperLAN CAC service. Specifies for a particular set of one or more shared radio channels the appropriate hierarchically independent channel access mechanism used by a HyperLAN CAC entity in a given HyperLAN. Uses the transmission and reception facilities specified by the HyperLAN physical layer. HyperLAN physical layer protocol. Provides the transmission and reception facilities to the HyperLAN CAC sublayer. Specifies for a particular set of one or more shared radio channels the techniques of transmission, reception, and channel assessment in a given channel. HyperLAN versions. HyperLAN has gone through versions like HyperLAN 1, HyperLAN 2. HyperLAN 1 started in 1991, was approved in 1996. HyperLAN 2 specifications completed in early 2000 were designed as a fast wireless connection for many kinds of network like UMTS, ATM, and IP networks. HyperLAN 2 operates in the 5 GHz band and offers up to 54 Mbits per second data transfer rate. The Media Access Control (MAC) protocol in HyperLAN 2 is Dynamic TDMA, which is used in the broadband wireless access standards like WiMAX. HyperLAN 2 offers better security measures than HyperLAN 1 as the data are secured with DES or triple DES algorithms. HyperMAN. A variant of HyperLAN is High Performance Radio Metropolitan Area Network (HyperMAN), also from ETSI and similar WiMAX. HyperMAN aims at provisioning broadband wireless internet access while covering a large geographic area. Highly optimized for packet-switched networks and readily supports fixed and nomadic applications. Fixed infrastructure network. Networking using switches, hubs, routers, access points, base stations, or gateways networked. Switches, hubs or routers locations are fixed. To connect to and access the network, a mobile device or wireless sensor has to be moved in the vicinity connectivity range of an access point. Example: a cellular network. Each mobile device or sensor connects to an access point, base station or gateway with a switch, hub or router A. Switch. In fixed infrastructure, switch provides connectivity between the two. A hub functions as a central switching exchange. Router provides two or more paths to route a message or packet so that the available path can be used at an instant. They function as the nodes of the network. A mobile device or sensor has to acquire an access point or node of the fixed infrastructure network before being able to connect to another. GSM cellular phones in a fixed infrastructure network. GSM system are three subsystems architecture consisting of radio subsystem RSS, network subsystem NSS, and operational subsystem OSS. Each cellular phone has to first connect to a RSS of GSM public LAN mobile network. Cellular phones in a fixed infrastructure network. The connectivity between two cellular phones is ensured through GSM public LAN mobile, PSTN, ISDN or PSPDN networks. Problems with fixed infrastructure network. Disconnection from the network and thus unable to communicate through the network when a wireless sensor or mobile device moves out of the range of access point, base station or gateway having the switch or router. Network not usable in operations like disaster relief. Fixed network infrastructure architecture. Mobile ad hoc network (MANET). A network in which the locations of the switches, hubs or routers can be mobile. The number of routers available at an instant can increase or decrease and the available routing paths can change. The mobile devices or wireless sensors as well as the access points can have switches or routers. An important characteristic of ad hoc network architecture is that its organization can change due to movement of a device or sensor. In other words, the ad hoc networks are self-organizing. The routes available to the mobile devices or wireless sensors can thus change at any time. Depend on presence and locations of other wireless devices in their vicinity connectivity range. Depends upon the location of the nodes, their connectivity, their service discovery capability, and their ability to search and route messages using nearest node or nearby nodes. MANET organization. The ad hoc network formed by the nodes A, C, D, E, F and G. Each mobile device or sensor functions as a node with a switch or router. The network organization changes if D and E move away from each other such that they reach out of the range of wireless coverage. Two new ad hoc networks will then be formed by 1. A, C and D and 2. A, G, F and E. The devices or two networks can still connect to each other through the common node A. Example: network of mobile device, home computer and printer at office. A Bluetooth-enabled mobile device, a Bluetooth-enabled computer, and internet with Wi-Fi connection at home. Assume that there is a Bluetooth-enabled computer connected to TCP/IP internet and also to JINI client printer at office. Through intermediate nodes Wi-Fi, internet and office computer, an ad hoc network establishment between the mobile device at home and printer at office when the user carrying the device moves from office to home and handheld PDA mobile device reaches near the home computer. A MANET establishes after the services of JINI, TCP/IP Bluetooth and Wi-Fi is discovered. When the user of same mobile device goes to an airport with Wi-Fi connectivity, a MANET again established with the office printer. MANET properties: seamless interaction and ubiquitous mobile computing environment. Seamless connectivity maintained between the devices when they move with the nearby wireless nodes, sensor nodes and embedded devices in automobiles. Neighbor discovery: one of the important characteristics of a MANET node. Data routing abilities: data can be routed from a source node to a neighboring node. Flexible network architecture and variable routing path to provide communication in case of the limited wireless connectivity range and resource constraints. Flexibility enables fast establishment of networks. When a new network is to be established, the only requirement is to provide a new set of nodes with limited wireless communication range. A node has limited capability, that is, it can connect only to the nodes which are nearby and thus consumes limited power. Using a service discovery protocol, a node discovers the service of a nearby node and communicates to a remote node in the MANET. Peer-to-peer connectivity. Computation's decentralization, independent computational, switching or routing and communication capabilities. Limited wireless connectivity range require that a node should move in the vicinity of at least one nearby node within the wireless communication range, else the node should be provided with the access point of wired communication. Weak connectivity and remote server latency. Unreliable links to base station or gateway. Failure of an intermediate node results in greater latency in communicating with the remote server. Resource constraints. Limited bandwidth available between two intermediate nodes. Node may have limited power and thus computations need to be energy efficient. No need of access point. Only selected access points provided for connection to other networks or other MANETs. Need to solve exposed or hidden terminal problem. Diversity in nodes: iPods, palm handheld computers, smartphones, PCs, smart labels, smart sensors, and automobile embedded systems. Protocol diversity: nodes can use different protocols, for example IRDA, Bluetooth, Zigbee, 802.11, GSM, or TCP/IP. Data caching, saving, and aggregation at node. Spectrum requirement at nodes in MANET. Large number devices connects to a centralized server. The bandwidth requirement is too high. N devices using FDMA in duplet transmission, then the required bandwidth will be 2 into N into FBW0, where FBW0 is the bandwidth allotted to one device for sending a packet to its access point. Using TDMA and SDMA, the bandwidth spectrum requirement is reduced. Each MANET node has much smaller frequency spectrum requirements than that for a node in a fixed infrastructure network. A node itself is a router for all the packets coming from or going to the other nodes. Nodes are themselves mobile. Therefore, bandwidth available to any node at any instant is variable. MANET enables spectrum reuse. Each wireless link provides a limited bandwidth. MANET communication is multi-hop. Each node has low and adaptable transmission power optimized to have signal strength just sufficient to carry the signal up to signal hop. Hops can therefore occur simultaneously using the same frequency band. That is spatial reuse of bandwidth. Also, the bandwidth depends on surrounding environment. The bandwidth depends on the number of next hop neighbors. The node with high number of next hop neighbors require higher bandwidth in FDMA. Mobile ad hoc network architecture. Node D at a given instant can get incoming packets from E, F, G and A and can send packets to C and A or vice versa. When node D transmits to G, it is through the three hops 1, D, E, 2, E and F, 3, F and G. The nodes D, E and G shall need higher bandwidth compared to C and F. Bandwidth required will be 2 into 3 into FBW0, where 3 nodes D, E or G can transmit in full duplay mode to all the nodes. Will be 2 into 2 into FBW0 for 2 nodes C or F. When each node path and each direction hop scheduled to operate at different instants as in TDMA, then the bandwidth required will be just FBW0. MANET nodes in multicast tree topology. Disseminates data packets and forms a multicasting network. Clusters of the nodes used to give a multicast tree topology in a MANET. Mesh network. Mesh-based mobile network offers highly dynamic autonomous topology segments for the robust IP-compliant data services within the mobile wireless communication networks. Inexpensive alternatives or improvement to infrastructure-based cellular CDMA or GSM mobile service provider. A multicast tree network differs from mesh as it provides only a single path between a sender and a receiver. Mesh networks, many paths. Mesh network of interconnected MANETs and fixed infrastructure network. Protocol for Unified Multicasting through Announcements PUMA. A protocol that builds a mesh that connects MANET nodes with each other. On the other mesh provides multiple paths between sender and receiver nodes. Need for PUMA. MANETs have nodes which may be mobile and the wireless links are error-prone. Certain packets may not be delivered to receivers through a multicast tree topology. PUMA, which sends packets from senders to receivers through multiple paths, may thus have a greater packet delivery ratio. However, in benign conditions, low mobility and traffic load, which leads to lesser collisions, sending packets is not needed and is a waste. In such situations, PUMA is able to reduce the redundancy. PUMA adapts the amount of redundancy in the network depending on need. Infrared Data Association IRDA. Infrared rays are invisible radiations of wavelength higher than that of red. An LED or a solid-state laser emits IR rays when given 10 to 20 mA current from a low-power battery or power source. When the ones and zeros are transmitted, the IR source current is modulated as per the ones and zeros. Direct line of sight IR from an LED detected at the receiver photodetector to get the data. The detector has 30° plus or minus 15° window to detect the incoming radiation. Used for remote control of TV. IRDA Infrared Data Association, a protocol for personal communication area network deploying infrared rays. IRDA features. IRDA applications. IR-based data transfer between a laptop computer and mobile handheld pocket PC when the two come in vicinity and line of sight of the IR receivers and detectors in each of them. Synchronization of PIM data, calendar, email, business card and text messages between a PC and mobile device or a device at cradle and IR COM port. Network characteristics. Point-to-shoot communication from peer-to-peer. IRDA device levels of communication. 5 levels of communication. Minimum, access, index, sync and SyncML, level 1 to 5. A level specifies a method of communication from simple to SyncML based. IRDA data transfer rates. IRDA 1.0 protocol for data rates up to 115 kbps. Data rates of 1.152 Mbps to 4 Mbps, 16 Mbps draft recommended. IRDA protocol layers. Layer 1 Physical. Data link layer 2A IR-LAP Link Access Protocol, 2B IR-LMP Link Management Protocol. Layer 3 to 4 Transport Layer Tiny TP Transport Protocol or IR-LMIAS Link Management Information Access Service Protocol. Layer 5 Session IR-LAN, IR-BUS, IR-MC, IR-TRAN, IR-COMM and IR-OBEX Object Exchange. Layer 6 and 7 Security and Application Software Layers as specified by the IRDA Alliance Sync PIM, Object Push PIM or Binary File Transfer. Session and Transport IRDA Protocols. IR-LAN for infrared LAN access. IR-BUS for access to serial bus by joysticks, keyboard, mice and game ports. IR-MC, IRDA Mobile Communication and Telephony Protocol. IR-TRAN, IRDA Transport Protocol for image or file transfers. IR-COMM, IRDA Communication Protocol by emulating serial, for example RS-232C COM or parallel port. Object Exchange IRDA Protocols. IR-OBEX for Object Exchange. Comparison of Bluetooth and IRDA. Network connection latency 3S for Bluetooth and a few ms for IRDA. Bitrate 1 Mbps for Bluetooth and 1.152 Mbps to 4 Mbps for IRDA. Protocol stack 250 kilobytes. Code size 50% down to 2% as compared to a Bluetooth device. FHSS for Bluetooth and serial synchronous, asynchronous or PPM for IRDA. Similarity of Bluetooth and IRDA. Efficiency used for low power short range transmission. Dissimilarity with Bluetooth. Bluetooth for wireless short range exchanges in mobile environment within 10-meter network. IRDA is for exchanges within a range of 1 meter in the vicinity of line of sight. IRDA has small form factor in radiation pattern and has 30° plus or minus 15° window. IEEE 802.11 standard. The IEEE 802 committee was set up in February 1980. That is the origin of the name, to set the standard for local area networks. IEEE later came up with different standards in the LAN domain. This includes all the layers from physical, media access and data link layer. When IEEE deliberated the standards for WLAN, it was clear that wireless LAN will be different only at the physical and media access layer. There were many WLAN technologies developed by researchers and industry driven by different motivations. Some of them were even standardized. However, Wi-Fi or IEEE 802.11 became the most popular WLAN protocol world over. Referring to 802.11 or IEEE 802.11 means the generic IEEE 802.11 WLAN family of standards. The 802.11 standardization originally published in 1997 with the goal to support 1 megabits per second and 2 megabits per second 2.4 GHz RF and infrared transmission. All other standards released following that were amendments to this original standard, with almost all the letters from the English alphabet starting from A to Z, like IEEE 802.11a, IEEE 802.11b or IEEE 802.11z. Different standards covered different aspects of WLAN like bandwidth, modulation techniques, physical media, security, roaming, etc. In June 2007, IEEE published the consolidated IEEE Standard 802.11 2007 standard entitled IEEE Standard for Information Technology, Telecommunications and Information Exchange between Systems, Local and Metropolitan Area Networks, Specific Requirement Part 11, Wireless LAN Medium Access Control MAC, and Physical Layer PHY specifications. This standard gives users in one document the entire IEEE 802.11 set of specifications for wireless local area networks, with many amendments that have been published till 2007. Multiple Access with Collision Avoidance MACA. MACA is a slotted media access control protocol used in wireless LAN data transmission to avoid collisions caused by the hidden station problem and to simplify exposed station problem. Proposed as an alternative to the traditional CSMA, CSMA senses the state of the channel only at the transmitter, which leads to hidden node problem. MACA uses RTS, request to send, and CTS, clear to send, to overcome hidden node problems and exposed node problem. Node which only hears CTS but no RTS stops from transmitting hidden node. Node which only hears RTS but no CTS is free to transmit exposed node. RTS and CTS carry the expected duration of data transmission. When there is a collision, it uses binary exponential backoff BEB before retrying. Figure below shows packet transmission in MACA. Multiple access with collision avoidance for wireless MACAW. MACAW is a slotted medium access control MAC protocol widely used in ad hoc networks. It is the foundations of many other MAC protocols used in wireless sensor networks. It uses RTS, CTS, DS data, ACK frame sequence for transferring data, sometimes preceded by an RTS, RRTS frame sequence, in view to provide solution to the hidden terminal problem. Does not make use of carrier sense. MACAW does not generally solve the exposed terminal problem. The binary exponential backoff can starve the flows. S1 and S2 have data to send. Let us say S1 captures the channel. S2 keeps sending RTS, but it gets collided. S2 increases backoff window. Gets blocked from transmitting longer period of time after every collision. Backoff change in MACAW. Sends backoff counter value in the packet. Nodes receiving the packet use the backoff counter carried in the packet instead of that used in MACA. This mechanism makes the bandwidth allocation fair. BEB, binary exponential backoff, adjusts the backoff counter very rapidly. MACAW introduced multiplicative increase and linear decrease (MILD). Per flow fairness is implemented. Each flow runs the backoff algorithm. Flow with minimum backoff value is chosen to send RTS. ACK packet in MACAW. In MACA, there was no reliability at DLL. It was left to the higher layer to provide reliability. MACAW introduced ACK packet for every data packet. If ACK is not received, the sender reschedules the data packet for transmission. Sender would send RTS. Receiver would send CTS if data packet was lost. Receiver would send ACK if ACK was lost. Data sending packet in MACAW. In MACA, an exposed node is free to transmit simultaneously when the source node is transmitting packets. But RTS transmission by exposed node is useless since the CTS reception will end in collision. So the source node sends a DS, data sending message, which contains the duration of data transmission. Tells the exposed node that an RTS-CTS was successful, hence need to wait until data ACK is done. S1 is already sending data packets to R1. S2 sends RTS to R2, but when R2 sends CTS, it collides with data packet from S1. RRTS, request for request to send packet in MACAW. S1 is already sending data. S2 sends RTS, but R2 does not respond with CTS since it is a hidden node to S1. S2 does not know the duration of the data transmission. R2 contends for the medium on behalf of S2. If it had received RTS from S2, then it waits for the next contention period and transmits RRTS. Node S2 on receiving RRTS sends RTS to R2 and normal RTS-CTS data ACK takes place. Point Coordination Function PCF. PCF is a media access control MAC technique used in IEEE 802.11 based WLANs. It resides in a point coordinator, also known as access point AP, to coordinate the communication within the network. It is based on a polling scheme. This polling scheme should be either a simple round-robin method or priority-based scheme. In PCF, a wireless channel has a superframe structure, contention-free repetition interval that consists of a contention-free period CFP and contention period CP. At the beginning of every CFP, the AP sends a beacon frame to all stations in the basic service area BSA after the AP confirms that the medium is idle for point interframe space PIFS. PIFS is smaller than a DIFS period but longer than the SIFS period. IEEE 802.11 defined the duration for different physical layers. Point Coordination Function PCF. All stations in BSS set their NAV and not to send any packet in the CFP after receiving a beacon. During the CFP, the AP polls each station in its polling list by sending a data plus CF poll frame or CF poll frame. If a station receives a data plus CF poll frame from the AP, it can respond to the AP after a SIFS period with a data plus CF ACK or a CF ACK frame. If the AP receives a data plus CF ACK frame, it can send a data plus CF ACK plus CF poll frame or CF ACK plus CF poll frame. If a station receives a CF poll from the AP, it can respond to the AP with data frame or a null frame. The AP continues to poll each station until it reaches the maximum duration of the CFP, and the AP can terminate the CFP by sending a CF end frame. ZigBee. For low transmitting power systems. Short-range wireless personal area network. Used for routing messages. ZigBee devices form a mesh network and use reactive and proactive protocols for routing. Enables applications in big-scale automation and remote controls. ZigBee is a suite of high-level communication protocols. ZigBee 1.0 specification released in December 2004. ZigBee devices conform to the IEEE 802.15.4 2003 Wireless Personal Area Network WPAN standards. ZigBee devices form a personal area home network for embedded sensors, industrial controllers, or medical data systems. Figure shows a network of ZigBee sensors, end devices, and ZigBee router devices connected to cellular network through an access point. It consists of three types of ZigBee devices: ZigBee coordinator, end devices, ZigBee router devices. ZigBee coordinator. Root node at each ZigBee network tree. It can connect to other networks and has full network information along with a store of the security keys for the ZigBee network nodes ZA in figure. ZigBee router nodes. Responsible for transfer of packets from the neighboring source to nearby node in the path to destination, ZB, ZC, and ZD in figure. ZigBee end device. Receives packet from a nearby node in the path from a source, ZE, ZF, ZG, ZH, and ZI in the figure. ZigBee network. ZigBee networks is one of two types: peer-to-peer, mesh. Peer-to-peer. For example, ZC, ZD, ZH network in which each node has a single path to neighboring node only. Mesh. For example, ZA, ZB, ZC network in below figure in which each node has a path to every other node. ZigBee devices. ZA, ZigBee end device. ZB, ZC, and ZD, a set of electric bulbs associates with the ZigBee routers. Each router in parallel. The set forms a peer-to-peer connection network ZE, ZD, ZC, ZB, ZA, with last one being Zigbee end device ZA. Zigbee coordinator ZG connects this network with other Zigbee networks, for example, of mobile handheld device ZE and ZF. The coordinator ZG also connects the access point for WLAN and provides internet connectivity to router ZJ for security system to cellular phone network and set-top box device ZH and screen ZI. Zigbee network router nodes ZE, ZF and ZG use mesh network connections. Basic features of Zigbee: radio frequency bands and modulation methods. ISM bands 2.4 GHz orthogonal QPSK, 915 MHz USA BPSK and 868 MHz USA BPSK. Zigbee device channels. For 2.4 GHz, there are 16 Zigbee channels. Each channel has frequency band 2400 plus 5 into n plus or minus 1.5 MHz, where n is equal to 1, 2 up to 15 or 16. Zigbee data transfer rates: 2.4 GHz at 250 kbits per second per channel, 915 MHz bands at 40 kbits per second per channel, and 868 MHz bands at 40 kbits per second per channel. Radio interface DSSS. Zigbee protocol layers: physical and a DLL data link layer part called MAC, media access control. Device types: coordinator, router and end device types. Routing protocol AODV. Protocol layers: physical layer as provided in IEEE 802.15, MAC layer as provided in IEEE 802.15, security and application software layers as specified by the Zigbee Alliance. Network characteristics: self-organization, peer-to-peer, mesh networks. Dissimilarity with Bluetooth. Bluetooth for wireless short-range exchanges in mobile environment. Zigbee for big-scale mesh network-based automation and remote control. Comparison of Bluetooth and Zigbee. Network connection latency: 3s for Bluetooth and 20 ms for Zigbee. Bitrate: 1 Mbps for Bluetooth and 250 kbps for Zigbee. Protocol stack: 250 kb for Bluetooth and 28 kb for Zigbee. Code size: 50% down to 2% as compared to a Bluetooth device. FHSS used for Bluetooth and DSSS for Zigbee. Similarity of Bluetooth and Zigbee. Both conform to IEEE 802.15 set of standards. Use of spread spectrum modulation results in spectrum efficiency in both. Use of 2.4 GHz in USA in both. Used for low power short range transmission. Both have small form factors radiation pattern. Conclusion. In this chapter, we have covered the following in detail. Basic MAC protocol CSMA CA. Infrastructure and ad hoc network topologies. MACA, MACAW. Use of PCF. IEEE 802.11 standards. Hyperlan. IRDA. Bluetooth. Zigbee.